Lots of questions on the BS7671 18th edition exam, and many of them on ZS and asking, how is it calculated? Why are there so many different ZS values in the books, and which ones to use? And many more questions. So, in this video, we will go a little more in depth and explain what we are trying to achieve, what the calculations are to achieve this, and how to use the various tables. One big question often asked, can I use the on-site guide for ZS answers in my 18th edition exam? A simple answer, no. The only book that you can take into an 18th edition exam is the Brown 18th edition Amendment 2 BS 7671 Wiring Regulations book. The answers to all the exam questions will be found in this book, all of them. In the exam, use the big brown book. This is Amendment 2, and this book gives ZS data, sometimes called ZS tabulated. Hopefully, you've already downloaded the Amendment 3 supplement to attach to it. If not, we will leave a link in the description to this video where you can download a free copy. The on-site guide, or OSG, gives ZSM, ZS measured data in the tables, and the numbers are not the same as in the regs book. You cannot take the on-site guide into the 18th edition exam. Frequently asked, how do we find the ZS data, and what does it mean? And everything we do now is from the Wiring Regulations book, and the page numbers relate to those pages in the Brown Amendment 2 book. There are two sections of interest to us. The tables in Appendix 3, beginning on page 409, that contain time and current data for different fuses and circuit breakers. They tell us how quickly they will operate for a certain amount of fault current. The tables in Chapter 41, beginning on page 62, will convert the time and current data into maximum earth fault loop impedance, or ZS, ZS tabulated. These tables answer the question, what impedance or resistance will allow sufficient current to flow to achieve disconnection of the breaker or fuse in a stated time for safety. Let's begin to find the data. This is the standard formula for calculating ZS and is easy to use. As shown in the yellow table, ZS is the earth fault loop impedance, a measurement of the circuit impedance from the furthest point of use along the earth or CPC all the way to the substation and all the way back again on the line conductor. U0 is the nominal AC voltage for the circuit. For a domestic property, this is usually 230 volts, even if we measure 240 volts. C-min is a voltage factor to allow for voltage fluctuations, and it makes an allowance for lower than expected voltages. And IA is the fault current required to cause the breaker or fuse to operate in the required time. Each type and rating of device will have its own IA. Now we can find the disconnection time required. Let's deal with final circuits first. A final circuit is a circuit that is connected directly to current using equipment or socket outlets. The last part of a circuit from the last fuse or breaker to a point of use, not counting FCUs. Regulation 411.3.2.2 gives guidance on which final circuits are affected. A maximum of 63 amps for socket circuits and a maximum of 32 amps for fixed equipment only. The regulation points us to table 41.1 on the next page. The table shows us the maximum disconnection times for certain circuits with certain voltage ranges. TN is shorthand for TNCS circuits and for TNS circuits. TT is just TT circuits. Be careful, our nominal voltage of 230 volts AC falls into the range of 120 volts to 230 volts. It is not in the next range up. Finding the disconnection time is easy. Take this scenario. A domestic property, final circuits with a 240 volt AC TNCS supply and nominal 230 volt AC. What is the maximum disconnection time? Following the instructions, we find that the maximum time is 0.4 seconds. Now that we know the time is 0.4 seconds, if we take a 32 amp BS7671 type B breaker, what fault current or IA must flow in order that it achieves a disconnection time of 0.4 seconds or less? Looking at the table on page 417, we can find 32 amps in the left column and IA is shown in the right column. A 32 amp type B breaker needs at least 160 amps of fault current to operate in the required time. We say that IA is 160 amps. That was for final circuits. Will the times be different for distribution circuits? Just below table 41.1 on page 65 are two important regulations: 411.3.2.3 and 411.3.2.4. A TN distribution circuit has a disconnection time of 5 seconds, and a TT distribution system must disconnect in 1 second. Remember where to find these regulations. They often appear in exams. Looking at the three tables, 41.2, 41.3 and 41.4, we notice that breakers and RCBOs only have one table for both final and distribution circuits. This is because the devices have been engineered so that they can respond to both disconnection times. Fuses work on a different technology and are manufactured to meet a much narrower range of response times. Therefore, there are two tables for fuses, one for final circuits and one for distribution circuits. Where you see 0.4 seconds disconnection time for fuses, assume a final circuit and table 41.2, and for 5 seconds assume a distribution circuit and table 41.4. Do not get tables 41.2 and 41.4 mixed up in an exam. It's easy to do. Let's go a little more into finding IA. Going back to page 417 and the type B breaker, we see a rather daunting graph filling the page. Good news, forget about the graph. We don't need it for what we are doing. We will concentrate just on the table at the top right. This will tell us all that we need to know. It will tell us the nominal rating or size of the circuit breaker and the minimum fault current that must flow through it if we want the device to operate and disconnect the supply in a time between 0.1 seconds and 5 seconds. It is now a simple task to find the breaker rating on the left and read IA on the right. The bigger the breaker rating, the greater the fault current that must flow. IA will increase, and this will affect ZS, the earth fault loop impedance. For a 16 amp device, IA is 80 amps. For a 32 amp breaker, IA is 160 amps. Different breakers or fuses will have different currents required with different trip times and a different IA. The faster the response time, the higher the IA required. Circuit breakers can be different too. There are type B, type C and type D breakers, and they all have a different IA requirement. This slide compares the type B and type C devices. A type B 20 amp breaker has an IA of 100 amps, whereas a type C has an IA of 200 amps. This is because a type C responds more slowly to fault currents and therefore needs a bigger IA to meet the required disconnection time. A type B 32 amp breaker has an IA of 160 amps and a 32 amp type C is 320 amps. A nice tip for breakers is that for a type B breaker, IA is 5 times the nominal rating of the breaker. For a type C, IA is 10 times the rating, and for type D, it is 20 times. Pause the video and check it out. Now we can make an example ZS calculation. The question might ask, a domestic property has a nominal 230 volt TNCS supply. What is the maximum permitted ZS in order to achieve a 0.4 second disconnection time for a circuit with a BS7671 32 amp type B breaker? We have all we need to calculate ZS for this circuit. We will use the standard ZS formula of U0 multiplied by C min and divided by IA. Putting the numbers into the calculator, we have 1.3656 and so on, which we can round up to 1.37 ohms. This is the maximum permitted ZS that will allow at least 160 amps of fault current to flow. A lower ZS will allow more current to flow, which is even better. Let's go now to table 41.3 on page 68. We can find type B breakers at the top, move along to 32 amp devices, and below 32 amps we find the maximum ZS, which is 1.37 ohms, the same as we have just calculated. The formula works. And now we have a table with all the calculations already done for us. Looking at the ZS tables in the wiring regulations book, we call these ZS tabulated values. The ZS numbers have come from these tables in this book. And there is good news as regards calculating ZS from the tables in Appendix 3. Unless it comes up as an exam question, which it will, there is now no need to find the minimum current for IA from Appendix 3. It's all done for us in the tables. If we need ZS, we can now go directly to the tables in Chapter 41. The tables are on pages 67 to 69, and it is important that we recognise the differences between them. The tables are laid out with fuses on one page, breakers on the next, and then back to fuses on the third page. Table 41.2 on page 67 is for fuses for final circuits with a 0.4 second disconnection time. Table 41.3 on page 68 is for breakers and RCBOs for final and distribution circuits, as these devices will achieve both 0.4 and 5 second disconnection times. And then there is table 41.4, page 69, for fuses for distribution circuits with a 5 second disconnection time. As a reminder, what are the differences between a final circuit and a distribution circuit? Shown here is a distribution board that is feeding a downstream consumer unit. The cable between the distribution board and the consumer unit is a distribution circuit. It is distributing electricity to a consumer unit, another set of fuses. From the consumer unit there are several sockets and lamps being supplied. These are final circuits, the last stage on the electricity's journey to the point of use. But notice that the distribution board also has a final circuit going to a lamp. A distribution circuit goes to another distribution board or a consumer unit, and there are more fuses downstream of it, so we have a 5 second disconnection time. A final circuit goes to the point of use. There are no more fuses and it has a 0.4 second disconnection time. A domestic installation is very similar. There is an intake position, main fuse and meter, along with the distributor's meter tails going to the house consumer unit. From the consumer unit, the circuits go out to all the points of use. There are no more fuses after the consumer unit. They are all final circuits with a disconnection time of 0.4 seconds. We don't count FCUs or fused connection units as valid fuses for this. For final circuits, ignore the fact that there might be an FCU for the central heating boiler. An exam tip: if an exam question says final circuit, assume 0.4 seconds disconnection time. If the exam question says distribution circuit, assume 5 seconds disconnection time. In certain circumstances, it may not be possible to achieve the maximum ZS values required. In those circumstances, an RCD may be used to achieve fault protection, subject to certain criteria, and this happens most often in TT installations. If the required maximum ZS cannot be achieved and other methods to reduce the ZS cannot be applied, then an RCD can be used to provide the fault protection required, but the ZS must not exceed the values shown in table 41.5 on page 70. Pause the video and take a moment to look at regulation 411.4.204 on page 69. But then we ask, where do the numbers come from? How do we get 1667 ohms? Look at regulation 411.5.3, which makes reference to earth electrodes and 50 volt touch voltages, since it is most often in TT systems that we cannot achieve the required ZS by normal means. Pause the video and follow the formulas as shown here. 50 volts touch voltage divided by 30 milliamps operating current of the RCD means that the ZS must be 1667 ohms or less. But an important note, RCDs are intended for additional protection and should be used for fault protection in high ZS circuits only after exhausting other methods to reduce the ZS of the circuit. This should not be accepted as the norm. There are many ways to achieve the maximum ZS values required. Permitted ZS can be by installing a different rating or type of breaker. Can the breaker be changed from 32 amps to 20 amps as an example? Type B breakers have a larger permitted ZS than a Type C or Type D. Actual ZS can also be reduced by installing larger CSA cable sizes or shorter cable runs. Look now at 55 volt and 63.5 volt circuits. Questions on this table often come up in exams, yet many people will never have looked at the table for these systems that apply to things like 110 volt centre tapped earth transformers or 55 volt systems. Table 41.6 on page 74 is where we should be. There's a section for circuit breakers and a section for fuses along the top, and a list of breaker ratings down the left hand side. As an example, we have a 55 volt single phase circuit that is protected by a 20 amp BS7671 Type B breaker. What is the maximum permitted ZS? Just follow the logical path. Type B circuit breaker, 55 volt single phase, IN, the rating is 20 amps. Read off the maximum permitted ZS, which is 0.52 ohms. The next question that we get asked is, how does this answer compare with maximum ZS for a 230 volt circuit? A 20 amp breaker in table 41.3 has a ZS of 2.19 ohms, yet this table shows 0.52 ohms. Please explain. We are talking about 55 volt systems here and comparing them to 230 volt circuits. So 230 volts divided by 55 volts and multiplied by 0.52 is a ZS of 2.18 ohms. Table 41.3 shows a ZS of 2.19 ohms for a 20 amp breaker, and 2.18 is close enough for me. A lower voltage of 55 volts needs a lower ZS to make sure the sufficient fault current flows. So will IA, the fault current, be enough at 55 volts? For a 20 amp Type B breaker at 230 volts, IA must be 100 amps minimum. Making an Ohm's law calculation using 55 volts and 0.52 ohms, we calculate that IA will be 106 amps. If you don't use table 41.6 in your work, there may be some confusion in an exam, so don't fall into the trap. Look at the breaker types C and D. At first glance, it looks like type C is 55 volts and type D is 63.5 volts. Wrong. This is not type C just for 55 volts and type D just for 63.5 volts. This can be 55 volts type C or type D and 63.5 volts for type C or type D. Remember this one, it catches many people out. And so to ZSM, or measured earth fault loop impedance. An exam question may ask for the maximum measured ZS, or earth fault loop impedance. In this case, we use the formula on page 410. It's the same formula that is used for ZS tabulated on pages 67 to 69, except we multiply the answer by 0.8, and this 0.8 is sometimes called the 80% rule. Let's do an example calculation, just in case it comes up in an exam. For a 32 amp type B breaker to disconnect within 0.4 seconds, a fault current, IA, of at least 160 amps must flow. The nominal voltage is 230 volts AC and Cmin is 0.95. What would the maximum measured ZS or ZSM be? Pause the video and take a look at the calculation. Our calculation here is 1.09 ohms, and when testing on site, this should be a maximum reading on your test meter. Compare this now to table 41.3 on page 68. Find 32 amps and we have 1.37 ohms, as we calculated many slides ago. If we multiply 1.37 by 0.8, we will have 1.09 ohms for ZS measured. So ZS tabulated from pages 67, 68, 69 multiplied by 0.8 will give us ZSM, or ZS measured. ZS values in the regs book multiplied by 0.8 are the same as the ZSM values in the on-site guide, or OSG. Just to be certain on that, in an exam, use the tables in the Brown wiring regulations book to find ZS tabulated, unless the question specifically asks for ZS measured, in which case multiply ZS tabulated by 0.8. This will give the same values as the on-site guide. Time for a few practice questions. 10 easy multi-choice questions for you to attempt yourself with the answers at the end. Pause the video on each slide and attempt an answer. It really is the best way to learn. Question 1 asks, what is the minimum fault current, IA, that must flow through a 16 amp BS 60898 type B breaker to achieve a disconnection time of 0.4 seconds? Choose the most appropriate answer, pause the video, attempt the answer and write it down before moving on. Question 2 next. Pause the video and have a go at an answer. On to question 3. A 30 amp BS3036 fuse protects a 230 volt AC final circuit with a required disconnection time of 0.4 seconds. What is the maximum earth fault loop impedance, or ZS? Question 4 now. Pause the video, find the answer, write it down. Question 5. A 230 volt distribution circuit is protected by a 20 amp BS88-2 GG fuse. To achieve a 5-second disconnection time, the earth fault loop impedance, ZS, should not exceed what? Pause the video, find the answer, and make sure you use the correct table. Question 6. All the information that you need is here, and the formula. Now to question 7. Pause the video and find the answer in Appendix 3. Question 8. How many seconds? On to question 9. Pause the video and attempt an answer. And finally, question 10. What is the answer? And here are the answers along with the page numbers where the answer can be found. In summary then, protective devices, breakers and fuses must operate within certain times as indicated in Chapter 41. Appendix 3 shows the minimum fault currents, IA, that must flow for the protected devices to operate and disconnect the circuit in the required times. Using the appropriate formula, we can calculate the maximum earth fault loop impedance, or ZS, for the circuit. Chapter 41 of the Wiring Regulations book also contains tables where the maximum ZS has already been calculated for the most common protective devices. These values are known as ZS tabulated. They come from the tables in the Wiring Regulations book. There is also a formula for ZSM, or ZS measured. This is simply the tabulated values multiplied by 0.8, sometimes called the 80% rule. ZS measured are the values that will be shown in the on-site guide. In the 18th edition exam, always answer questions with the tabulated values as found in tables 41.2, 41.3 and 41.4, unless specifically told in the question to give ZS measured answers. ZS measured is what you will measure on site with your test equipment. Thank you for watching. It really is appreciated, and I hope that you found this video both useful and informative with a little more knowledge in your mental toolbox. Please subscribe to our channel to get access to all of our videos, and remember to click on notify to be sure of not missing our next video. And don't forget, you can type in Learn Electrics into the YouTube search bar to go directly to our channel at any time from any computer or smart device. We are always adding new videos to our channel, so don't miss the next one. And once again, thank you for watching, and we hope to see you again very soon.